Hello friends, it is Ben again. This is a video for the Math Tech class and it's looking at what we're doing on day 3. As you'll remember from last time, these videos are designed for you to run through if you don't really know how to do some of the stuff that you're being asked to do. If you already know how to do it, you can get this done a lot faster, okay? So in any case, I'm going to take a look here at the assignment for day 3, like I said, and this is looking at some data analysis stuff. It's not everything about data analysis, but it's just showing you a few tricks that come in handy. I think these ones are about stuff from the statistics class, which might also be relevant to stuff that you would do in the sciences. Okay, all this stuff is really intended for that kind of thing. All right, I'm going to share screen here and bring up the Excel document, which you're going to be doing stuff with. All right, now, as I mentioned on the previous assignment, I always take and edit mine a little bit. I don't want to give you the exact same thing as what you're watching me do because, you know, in particular for this, I trimmed down the number of things in the little chart here, and they're a little bit different. So, it's slightly different data. Okay. So the first page of it is titled binomial data, and it is a bunch of stuff that says either red or blue. Yeah, I just had a computer randomly generate that. The second page is some normal distribution data, and we're going to be looking at, I forget. Right, we're going to be looking at doing the data analysis of deciding whether or not this mean and to a lesser degree the standard deviation actually fit for the data. The way I got the data, again, was to just tell a computer to generate data that actually did have that mean and did have that standard deviation. But there's a random element to it. And so I want you all to see an example where you're trying to establish whether or not you've got strong enough evidence to say, sorry, whether or not you've got strong enough evidence to say that it's not from this distribution. In this case, it is. I'm being straightforward with you about that. Then the last set is also taken from a normal distribution, but as a matter of fact, the same normal distribution, but the task that we're going to look at is actually trying to establish whether it really looks like it's from a normal distribution. These are all things that would just be day-to-day tasks that you might, in some adapted manner, be doing with data in a lab. All right, so the first one, I am going to claim to you that the proportion of red, proportion of reds that I was generating with is 40%. So I'm typing in here the 0.4. I'm saying my p-value was 0.4. Matter of fact, I'm going to be typing lots of stuff here that are words and lots of stuff here that are numbers, and I would like them to sit next to each other. So I'm going to say that the p is equal to 0.4. As a matter of fact, with what we're working with, it might even make sense to go there to that B12 and just name that P. Okay. All right. Then the thing that we're going to want to do is to count how many things we have there. Yes, I know. You can just look and see. It's 10 wide, it's 10 high, there's 100 of them. But you might sometimes have use for this thing here, so I want to show it to you. So equals count A1 colon A10. All right. Close parentheses. Now, Oh, I said the wrong thing. I said A10 and I meant J10. Close parentheses, enter. And you'll notice that it came back with an answer of 0. I also put it in the wrong spot. So why did it come back with 0? Well, the things you're counting are words. And the count function actually counts the number of numbers that appear. So I'm going to delete that. I'm going to say this is going to give us the n that this has. I'm going to instead, because I'm counting these words, I'm going to say count A. The count A is for count alphabetic. And now we'll say A1 colon A10. Did it again. You know what? It might be smart for me to actually go through and name that, huh? All right, so I'm going to here count the number of reds, and I'm going to here count the number of blues. Oops, blues. All right. Now, the thing here is we're going to use the COUNTIF. We've already seen that the COUNTIF function will actually count things that are alphabetic. Remember when we did the male, female, and the Democratic, Republican counts on the previous assignment? So equals COUNTIF and A1 colon J10, comma, and then the criteria has to be a quotation mark and equals, and we'll have red. You know, I don't know the answer to something. If I said capital RED, I wonder if this is case sensitive. Turns out it's not. Huh. Okay. So there are 29 of them that are red, and so you could guess the number that'll be blue, but I'm going to go ahead and tell it to do it again. A1 to J10 and equals blue. All right. So now in the stat class, when we check, when we get a sample and try to figure out what the p-value is, the thing that we call the experimental value for p is not p, but rather p hat. And I put a dash in there because otherwise it looks like I'm writing fat, and that sounds like the kind of word that cool people used to use to describe some things. And I was never cool, and now I'm old on top of that, so I should not use cool words, even old cool words. All right, so anyway, that p hat that you get, we're going to say equals, we're talking about the reds. And so I clicked on where the red count was, divide by, and then I'll click on where the n is at, right? Could you have just typed 0.29? Yes, totally. But now we have the advantage that if somebody came along and dumped new data here, we could just immediately make that change. Now, the thing that you need to be noting out of this is, hey, that really does not seem like we got a p hat that matched up very well with that p. That's true. I lied to you. I generated this data with a p-value of 0.3. But I did that so that we could look at how you show that you've got a p hat that doesn't match. Okay. So the thing that we're going to do is to use something called a binomial distribution. Okay. And in the instructions for this, I refer to it as, I think, binom dist. So that hopefully will help us out in figuring this, figuring out how to use it, right? So I'm going to come over to this next column here where I'm going to put some more stuff. And I'm going to do that same thing about left and right justifying. But here I'm going to just, as my description say, that I'm going to get the probability that we would get an X value that was less than or equal to our, I wanted to say P hat, but we're going to talk about N times the P hat. Oops, P hat, parentheses, equals. Okay, so you see how that's just saying what we're getting for that. And then I'm going to go down a little bit there and figure out almost the same thing, but the probability that we would get an X being greater than or equal to that NP hat. Okay, so the NP hat is going to be that value that we got there, the 29, and we got it from just counting. So we're using a binomial distribution. We say equals binom, and fortunately the helper comes up and says, do you mean binom dot, and gives me some options. I'm going to say binom dot dist, parentheses, and then it says number underscore s. Oh, that's takes me some thinking to figure out what's going on with it. The number must be in reference to the number we're talking about that we got, right? Trials is going to be the N value. And then the probability underscore S, the probability is going to be that P value up there. And the last thing is the cumulative, and that's going to be a true or false. Okay, so going through what we do here, the number that we talk about is the 29. I'm just going to click on it, put a comma after. The number of trials, the N value, I'm going to click on that. And the probability that P, it went ahead and called it P. Yay! So we could have just used that there as well. It's going to come up later though. So that's why we named it. And comma, this cumulative thing, right now I'm going to type false. Okay, and just hit enter. Now that's a relatively small number, but that is the probability you would get exactly 29, which is not what we want. The cumulative, by setting it to be true, will actually add up all those probabilities from 1, 2, 3 on up to 29. Some of those numbers are super duper small, and but when you add them all up, you get this 0.014 or something. Your number will be different, okay? All right, then the other thing that I want us to see how to do is to get the probability that X is greater than or equal to something, okay? And there's a trick involved. Now, if I'd said just greater than, you could just say 1 minus the thing that's above, okay? But because we're talking about this binomial distribution, which, is counting things, if I say greater than or equal to, I want to include the 29. See how that's tricky? So I say 1 minus, oops, nope, I don't. I say equals 1 minus. And then I say the binom dot dist. Okay, now here's the tricky thing. Because I said 1 minus, I'm going to be taking the opposite. And that means it will throw out the things that I'm looking at doing less than or equal to, okay? So if I want to talk about the numbers that would include the 29, then I need to go 1 down and not include the 29, so that when I take the opposite and kind of flip it around, that my not including the 29 will turn into including it, okay? So what I'm going to do is to click there on that B16 and say -1, because now it'll be 1 less. And then The number of trials is still 100, and the P is still 0.4, and we are still going to want things that are cumulative, okay? But anyway, notice that you get a much larger number, and the thing is that most of the possible things that you might get out of one of these distributions are going to be close to the 0.4 times the 100. So the numbers are mostly going to be greater than, or the numbers are mostly going to be close to 40. And we're saying, let's get all the numbers that are greater than or equal to 29. That's going to include most of the numbers, right? So in any case, though, then that is the less than or equal to, oh, and let me demonstrate real quick how we could get the probability that X is less than in P hat and the probability that X is greater than the N P hat. Okay, so if you wanted to strictly leave things out, now we saw before here what we could do to get less than or equal to. So I'm going to actually try to use that code, but I've got to kind of remember it, because remember, if I copy it, it will move everything down. So I've got to remember it. So equals binom dist, and I choose the 29 there, and I want to not include the 29. So I say -1, okay, comma, and then the number of trials is the same, probability is the same, and we want to say true to get it to be cumulative. And the same sort of thing here. Although, you saw how I did that there, okay? Now I'm going to do something, and it should not change the number. So keep track, it says 0.084 something. I'm going to say instead equals 1 minus the greater than or equal to 1. Look, it got me the same thing. And so equals 1 minus, now we want to get greater than, so we can take the opposite of the less than or equal to 1 and get that there, okay? So those are all these probabilities that we might think about on this, right? Then there is another thing it asks you to do in the homework, and that is the probability X is not equal to. I don't really have a key for that, but later on you'll see that programmers use exclamation point equals to mean not equal, and then the NP hat. Now, the thing that we are going to do for that is to look at the probability, and it depends on what you are talking about usually, but we're going to talk about the least of those values, which is generally going to be one of the less than or greater thans, okay? And we are going to have 2 times that minimum from those. And I can just take and say it's the minimum of those 2, right? Now, the thing is that what we're doing is looking at this probability that you get extreme cases, right? And so consequently, we're thinking about probabilities that happen out on the ends. And when we do this and do the not equal to part, we're doing something called a two-tailed test. And technically, we ought to do a little more than just saying 2 times the minimum and stuff. But yeah, anyway, but the 2 times the minimum is going to get the probabilities that things would be extreme in the way that they're looking right there, or extreme in the opposite direction. Okay. And so what we are actually calculating is the probability that somebody would get the number that we did with the p-value and the n-value being what we know they are, or yeah, with the p-value being what we claim it is and the n-value being what we know it is. Okay, so here we have gotten that the probability of having this happen is 0.0168 blah blah blah, so about 1.7%. That's a pretty low chance of having the thing happen that you know did happen. And that suggests maybe something's wrong with our assumptions, our polarized assumptions, that n was 100 and p was 0.4. We know n's got to be 100. So this leads us to suspect, because we got a low probability of the thing happening that we know did happen, that our assumption that p was 0.4 is probably wrong. Okay, so when you do this in a science class for lab stuff, we often refer to p-tests and p-values. And if the p-value is if the p-value is less than 5%, that's usually the rule of thumb people tend to use, then we tend to think that our assumption about the data was wrong. So, all right. So that is really the sophisticated kind of way to go about this. Let me go ahead and show you another way of going about it, but it's something that it's something using what's referred to as a normal distribution. And so in order to talk about a normal distribution, I want to jump over here to a different window. And yeah, okay, well, maybe I actually need to go find that window and make sure it's working. There it is. Okay, so all right, so share screen, normal distribution. All right, so normal distribution is something that we use the hell out of in the sciences. And it is a curve that looks kind of like this. It's a bell-shaped curve. And and the total area under that curve ends up being 1. And if we are looking at something that is normally distributed, we can figure out the probability that we would have an x value fall into a certain area by looking at the area like between 2 x values. Okay, so one thing to see here, I'm going to zoom out a little bit, is that I have taken and I'm going to turn off the shading there. I can have this normal distribution be centered wherever I want it to. Okay, for purposes of something we'll look at later, I wanted to have it at 50, but then that, okay, so that's that top of the curve there being at 50, we refer to that as being the median, which means half of the area is below it, half is above it because it's symmetrical. But the median is 50. And it turns out that the mean is also 50. That's more statistical stuff. But also the mode, which is the place that is the highest on the distribution. Okay, and so I can adjust that, I have this other adjustment that's referred to as the standard deviation. If I make it smaller, the graph has to get skinnier and taller. If I make it larger, then the graph has to get flatter and wider. And that sort of accommodation is because of the fact that it has to have an area of 1. In order to keep the area being 1, if it gets skinnier, it has to get taller. Kind of like if you've ever squeezed a water balloon, you know how it kind of squeeze out one end or something. So, but with regard to the area stuff, we have things built into, excuse me, we have things built into Excel. And if you've ever dealt with a TI calculator, these are built in there as well in order to take and set 2 X values and figure out what the area is between them. Okay. So with that sort of idea in mind, we're going to use something called a normal distribution function. And go back to this. All right. So in order to do that, then we're going to have to know what the mu is equal to. Oh, I did not center that. All right. And what the sigma is equal to. And I gave you formulas for this that you'll refer back to because nobody remembers this stuff unless they deal with it every day. But the mu for what we're going to deal with is simply going to be the p-value, okay? And the sigma for what we would deal with is going to be a little harder. It has a formula that is square root. The abbreviation for that is SQRT parenthesis. And then you need to take your p times, you have to type the times. If you don't type the times, it will give you an error. But times the 1 minus p, 1 minus p. But then you need to divide it by the n value. Okay, close your parentheses and it will calculate it. All right, so this is going to be representing the distribution that we would have about the probability that we would get a p hat that was less than or equal to what it is that we're dealing with. Okay. So coming along here, I'm going to actually type in probability that p hat is, that probability that we would get an x that's less than the p hat is equal to this. Okay. So now the normal distribution equals norm.dist parentheses. And if you can read that, which you probably can't unless you zoom in, it has an x and then a mean and a standard deviation and cumulative. So with normal distribution stuff, you always have to be dealing with cumulative. It doesn't even make sense to not. And so I don't know why that's something that they have you worry about. But we're going to get the normal distribution. Yeah, actually, you know what? I'm going to hit escape. I'm going to come over here to the p hat, and I'm going to name it. I'm going to call it. I can't really use the dash in it, so I'm going to type p hat. So fat, yeah. But now when I use this, I can say the norm dist. So the probability that my x's that I'm thinking about are less than that p hat, given that the mean was actually this mu, and the standard deviation was this thing here, and we're going to go ahead and have that cumulative. All right. See how the numbers that we got for the less than for p hat and the less than or equal to for n p hat are almost the same thing. Okay. All right. So I'm going to go ahead and do these other bits that we've got here. Oh, wow. I just realized I'm going to have to go to class. Okay. All right. So let's finish this bit up and then be done. So the thing that we don't have to worry about with normal distributions that we did with binomial distributions, the or equal to doesn't make sense to talk about. It's the exactly equal to stuff is only going to end up giving you zeros, all right? So consequently, you can just say 1 minus the thing that you just got, or the probability of the greater than or the greater than or equal to, okay? And so when we come down here and want to say something about the probability that the x is not equal to p hat, we're going to do a lot the same trick that we had down here. We're going to say it's equal to 2 times, and then we're going to take the minimum of those two things. Okay. Now the thing is, if you had the maximum of those two things, you would actually get a value that's greater than 1. And probabilities are never greater than 1, ever. So if you tell somebody you have a probability that's, what would be like 1.97 or something, they'll go, oh, you don't understand probabilities. And they'll stop paying attention to you. And that can be kind of bad. But notice we ended up with a 0.0247. Now that's not very close to what this is down here that we got out of the binomial distribution. But here's the funny bit. If I take that stuff that has the less thans and replace it with the stuff that has the or equal tos, now we've got 0.02955 and 0.0247. This number down here, or this number here, and this number here are pretty close to each other. And it will always be the case that this number that comes from the normal distribution gets you a little bit of an underestimate. And this one here, yeah, I said that backwards. Apologies. No, I didn't. So the normal distribution will give you a little bit of an underestimate if you're using the or equal tos. And it gives you an overestimate if you're using the strictly not equal tos. Okay. So when you are testing these proportions, these sample proportions, you have to be super clear about what it is that your criteria for testing are about. Does it include the one that is equal to or not? In general, I believe you'll find that it is going to include it, but in a stat class, they always use this method here that has a normal distribution in mind. I'm going to move this down a little bit. And yeah, make sure it didn't change anything. So I'm using normal probabilities. And then I'm going to over here label this one using binomial probability. And I think, yeah, I'm going to center that one there. And I'm going to then take these and move them up a little bit so they're a little easier to read. Okay. this is the deliverable out of this portion of things. I'm going to actually cut this video short and make a second video about doing the second page. Yeah, it'll be shorter. So anyway, I will see you all in a bit. Both, yeah, I'm actually about to go to your first class. So yay, talk to you soon.